Somewhere behind your closed eyes, a very small, very patient part of your mind is still keeping track. Not of anything urgent, just the rise and fall of your breath, the soft weight of the blanket, the quiet tick of seconds you're not really counting but could if you wanted to. That capacity, the one that could keep going, keep adding one more, and then one more after that, is where we're going to spend the next little while. Not to reach anywhere, just to notice what it feels like to continue. Try this, gently, without any real effort. Picture the number 1, just the shape of it, sitting alone in a soft, dark room. Now let it become 2, then 3. You don't have to do this quickly or even clearly. Let the numbers blur a little, the way headlights blur on a rainy window. 4, 5. Notice that at no point does anything stop you. There's no wall you bump into, no door marked no further. The next number is always just there, waiting, the way the next stair is always there under your foot, even in the dark, even when you can't see the bottom of the staircase. You could stand at the top of that staircase for a long time, feeling for the edge of each step with your toes, never once finding a step that refuses to be followed by another. This is one of the oldest and gentlest facts about counting, and people have known it for a very long time, long before anyone had a word like infinity to hang on it. A shepherd in ancient Mesopotamia, keeping track of sheep with small clay tokens, didn't need a philosophy of endlessness to understand that there was always room for one more sheep, one more token, one more mark scratched into a stick. Archaeologists have found these tokens by the thousands, small clay cones and spheres, pressed into soft tablets or strung on cords, each one standing in for a single animal, a single jar of oil, a single measure of grain. The system was almost embarrassingly simple. It didn't need a concept of a largest number because the shepherd never asked what the largest number was. He only ever asked whether there was one more sheep to account for, and the answer, whatever it turned out to be, could always be represented by one more token. The counting itself never announced its own completion. It simply continued for as long as there were things to count, and when the sheep ran out, the counting stopped. Not because the numbers ran out, but because the sheep did. That's worth sitting with for a moment, because it's the first quiet distinction we're going to draw tonight, and it doesn't need to be dramatic to be important. The numbers didn't run out, the sheep did. The counting process has no natural ending built into it. It's the world, tired legs, finite flocks, the setting sun, that puts a stop to things. Left alone, counting is like a path through a forest that keeps unrolling ahead of you no matter how far you walk. You never arrive at the last tree. You just eventually turn around, or sit down, or fall asleep before you find out what's further on. Picture that forest path now, if it helps. Soft ground underfoot, the trees thinning and thickening in no particular pattern, no signpost anywhere promising an end. You're not lost. You're simply walking somewhere that was never built with a final tree in mind. The Greek philosopher Aristotle, writing in the 4th century BC, noticed something very similar and gave it careful, precise language. Language people still use today, even if they don't know they're borrowing it from him. He was working at a time when Greek mathematics was becoming unusually rigorous, unusually careful about the difference between what could be shown and what could only be assumed, and infinity was one of the places where that carefulness mattered most. He drew a line between two ideas that sound almost identical, but aren't. One he called potential infinity, the endless possibility of continuing, of adding one more, of there always being a next step available. The other he called actual infinity, a completed, finished collection that already contains infinitely many things, all at once, the way a shelf might already hold every book that will ever be written, sitting there in front of you. Done, spines facing out, nothing left to add and nothing left to write. Aristotle was comfortable with the first idea and deeply uneasy about the second. He thought potential infinity was simply a fact about processes, counting, dividing, walking, that they could always continue further. But an actual infinity, a completed infinite totality, just sitting there as a finished object, struck him as something nature never quite handed you. You could always cut a piece of bread in half, and then in half again, and again, without any final, smallest crumb waiting at the bottom. Imagine doing this slowly, at a kitchen table, late at night, having a piece of bread over and over, with no particular goal, each piece smaller than the last, each cut just as possible as the one before it. You would never hold, in your hand, the completed, infinite set of all those cuts, all the crumbs that could ever exist gathered together at once. You'd only ever be midway through cutting, one small piece resting in your palm, the rest of the process stretching ahead of you, unfinished, patient, indifferent to whether you continue or stop and go to bed. You don't have to decide tonight whether Aristotle was right. Mathematicians in later centuries would come to disagree with him in interesting and careful ways, and we'll get to some of that slowly, without any rush, in the sections ahead. For now, it's enough to simply feel the difference between the two ideas, the way you might feel the difference between a hallway that keeps extending in front of you as you walk, and a hallway that someone tells you is, right now, infinitely long, stretching away behind a closed door you haven't opened yet. The first is a process, something happening, something you're inside of. The second is a claim about a finished thing, something already true whether you walk toward it or not. Let your mind go back to the counting, if it likes. 1, 2, 3, drifting upward with no particular hurry. Notice that this is a very ordinary, very human experience, the sense that you could keep going. Small children discover it on their own, usually with some delight, when they realize that no matter how high they count, they can always add one more. A child might count to 100, out loud, a little breathless with the effort, and proudly announce that they've counted all the numbers, certain they've reached some kind of summit. And then a parent, gently, almost playfully, might ask, what happens if you count one more, 101, and after that, 102? The child usually laughs because something has been revealed, not a fact they were told, but a fact they noticed for themselves, in their own voice, in their own counting, the way you notice that a mirror facing another mirror seems to hold an endless hallway of reflections, each one smaller and dimmer, without any obvious final image at the back. That mirror trick is a nice thing to hold in your mind here, because it captures something true without asking you to do any math at all. Stand two mirrors facing each other. Most people have done this at some point, in a bathroom, in a dressing room, in a barbershop chair, waiting with a towel around their shoulders, and you'll see reflection after reflection, curving away into a soft green-tinted distance, each pane of glass adding its own faint shadow to the last. You never actually see infinitely many reflections. Your eyes give out, the light gets too dim, the image blurs into nothing after a few dozen repetitions, swallowed by the glass itself. But something in you understands that the pattern doesn't stop there. It's not that the mirrors decided to stop reflecting after the 40th image, as if they'd grown tired. It's that your ability to perceive it simply ran out first. The dimming light, the limits of your own eyes, not any limit belonging to the mirrors themselves. The endlessness was never really about what you could see. It was about what the process, left alone, would keep doing forever, indifferent to whether anyone was standing there to watch it. This is close to what mathematicians mean, most of the time, when they talk about a sequence going on forever, the count of natural numbers, the reflections in the mirrors, the steps down that dark staircase, the halved and rehalved piece of bread. It's a process without a built-in stopping point, not a mysterious finished object hiding somewhere out past the edge of what you can imagine. And there is something quietly restful in that idea, if you let it settle over you the way a blanket settles once you stop adjusting it. You are not being asked to picture a completed infinity tonight, some vast finished shelf holding every number at once, every book already written. You are only being asked to notice the calm, ordinary fact that counting doesn't ask permission to stop. It simply continues, patiently, for as long as you're willing to follow it, and then it waits for you, unfinished and unhurried, for whenever you'd like to pick it back up, tomorrow, or in a dream, or never. It makes no difference to the counting itself. Later on, we'll gently open that other door, the one Aristotle was more wary of, the one about collections that are already, somehow, complete and infinite all at once, the way mathematicians eventually learned to think about the entire endless list of counting numbers as a single object, a whole thing, rather than a process still underway. That idea took much longer for human thought to feel comfortable holding, centuries longer, and it will take us a little while too, without any rush, the way sleep itself takes its own unhurried time to arrive. Think for a moment about the oldest argument in the world, the one that happens on playgrounds and in car back seats, and in the hush, just before children are supposed to be asleep. One says 100, the other says 101. One says 1,000,000, the other says 1,000,001, and then, triumphantly, 1,000,002, as if the extra digit settles something important. It never quite does, and somewhere around the 10th round of this, a child usually arrives, half by accident, half by instinct, at a small and genuinely profound discovery. Whatever number you say, someone can always say one more. There is no way to win the game by naming a biggest number, because the rules of counting themselves forbid it. Add 1 to anything, and you get something new, something larger, something that didn't exist in your list a moment before. The biggest number a person could ever say is never actually the biggest number. It's just the last one they happen to have breath for. This is worth sitting with slowly, because it is stranger than it first sounds. In almost every other part of life, things run out. A jar of water empties. A hallway ends in a wall. A staircase, however long, eventually meets a landing. Our whole sense of what a collection is comes from experience, with collections that have edges. A bookshelf, a drawer of socks, a field of grass that stops where the fence begins. Even very large things end. The number of grains of sand on a beach is enormous, almost incomprehensibly so, and yet it is still a number, still something you could, in principle, finish counting, given enough patience and enough centuries. The ancient Greek mathematician Archimedes actually tried something close to this, in a short work he called the Sand Reckoner. He set out to calculate roughly how many grains of sand it would take to fill the entire known universe as the Greeks understood it, and he needed to invent new ways of naming numbers just to get the figure onto paper, because Greek numerals of his day simply hadn't been built to reach that far. He succeeded. He got a number, an unfathomably large number, but a number nonetheless, with a beginning and an end, sitting there complete, like a very long train with a caboose. The whole numbers don't work that way. There is no caboose. However far Archimedes traveled with his sand grains, the counting numbers were still there ahead of him, patient and indifferent, unbothered by how large his number had become, ready to keep going exactly one more step. This is the part where your intuition, trained its whole life on jars and hallways and staircases, quietly starts to struggle. Not because the idea is logically complicated, it's actually one of the simplest proofs in mathematics, but because nothing in your ordinary experience prepares you to trust a process that genuinely never runs out. Suppose, just for the sake of argument, that there were a largest whole number. Give it a name if you like. Call it n. Now ask what happens if you add 1 to it. N plus 1 is a whole number too, and it's larger than n. But we said n was the largest. So either n wasn't the largest after all, or the whole idea of a largest number doesn't hold together in the first place. That's the entire proof. It takes about 10 seconds to say, and yet it settles something that feels, emotionally, like it ought to require more effort. There is no largest whole number, not because we haven't looked hard enough, but because the very act of finding one would immediately create a larger one, forever, no matter how many times you tried. Human minds, it turns out, aren't naturally built to hold this kind of fact comfortably. Researchers who study how people perceive quantity have found that we can glance at a small handful of objects, 3 coins, 4 candles, 5 sheep in a field, and simply know how many there are, instantly, without counting. Cognitive scientists call this subitizing, and it seems to be almost automatic, something even very young children and, curiously, some animals can do. But that fast, effortless sense of quantity falls apart quickly. Somewhere past 4 or 5 items, you stop simply perceiving the number and start estimating it, or counting it out one by one, translating the world into the slow, deliberate language of numerals, because your perception alone can no longer keep up. Infinity, then, isn't just a big version of 5. It isn't a bigger handful. It's a completely different kind of thing, one that has nothing to do with how much your senses or your intuition can hold at once, and everything to do with the shape of a process that simply refuses, by its own internal logic, to stop. And this is where an old and useful distinction becomes worth having in your pocket, one that goes back, in its clearest early form, to Aristotle, writing in the 4th century BCE, in a set of lectures we now know as the Physics. Aristotle was comfortable with infinity in one particular sense. He accepted what we now call potential infinity, the idea that a process, like counting, or dividing a length of rope in half again and again, could always continue. There was always a next step available. Nothing forced it to stop. But he was deeply uneasy with a different idea, what we now call actual infinity. The notion that an infinite collection could exist all at once, complete, finished, sitting there as a single whole object, the way a finished bookshelf sits there with all its books already on it. To Aristotle, that felt incoherent, maybe even impossible. A process could go on forever. But an infinite thing, fully assembled and waiting, that seemed like a contradiction dressed up as an idea, as if you asked someone to hand you a staircase with infinitely many steps, all already built, right now, on the table in front of you. For a very long stretch of history, this caution served mathematicians well, and it also quietly limited them. If you were only ever allowed to think of infinity as a process that could always take one more step, then certain questions became awkward to even ask. Is the collection of all whole numbers, considered altogether, bigger than the collection of all even numbers? It's a strange question if you're only permitted to think of counting as something still happening, still underway, never finished enough to compare against anything else. You can't easily weigh 2 things on a scale if neither of them is ever allowed to be a finished, sittable, comparable thing in the first place. So for centuries, careful thinkers tiptoed around actual infinity, treating it the way a nervous swimmer treats deep water, fine to look at from the shore, uncomfortable to stand in. There's something almost tender about that caution. In hindsight, it wasn't foolishness. It was honesty about the limits of intuition, an unwillingness to claim more certainty than the mind could actually support. And it mirrors, in its own way, the quiet, patient feeling of lying still at the edge of sleep, aware that thought is about to change its shape, not quite ready yet to let it. Later, we'll meet the people who finally worked up the nerve to wade into that deep water on purpose. Mathematicians who found a way to treat the whole endless list of counting numbers as one completed thing, and who discovered, once they did, some of the strangest and gentlest surprises in all of mathematics. But that is still a little further down the dark, comfortable staircase we're walking together tonight, one slow step at a time. Long before anyone worked up the nerve to imagine an infinite staircase sitting complete and waiting, there was a quieter, older worry about infinity, and it didn't come from arithmetic at all. It came from something as ordinary as walking across a room, as ordinary as the short walk you might take tonight from a doorway to a bed, sheets already turned back, lamp already dimmed. The man usually credited with turning this everyday worry into something unforgettable was Zeno, who lived in the 5th century before our era in a small town called Elea, perched on the coast of what is now southern Italy, a place of olive groves and quiet harbors where philosophy was still young enough that a clever argument could genuinely rattle people. Zeno was a devoted student of the philosopher Parmenides, a thinker who held a belief that most of his neighbors found close to absurd, that change and motion were illusions, that beneath the flickering, shifting surface of the world, reality was actually still, whole, and unmoving, a single, unbroken thing pretending to be many separate moments. People pushed back, naturally, and who could blame them? You watch a candle gutter and shrink, its light narrowing by degrees. You watch your own breath rise and fall while you drift toward sleep, chest lifting, chest settling, over and over. Motion seemed like the last thing anyone could reasonably doubt, the one fact so plain it hardly needed defending. So Zeno, apparently out of loyalty to his teacher, set out to defend the idea not by arguing directly, but sideways, by showing that the alternative, the world as we ordinarily picture it, full of confident motion, led to contradictions just as strange, just as maddening, as anything Parmenides had proposed. His most famous argument imagines a race between the swift warrior Achilles and a slow-moving tortoise. Picture a dusty track somewhere in ancient Greece, warm sunlight lying flat across packed earth, a small crowd murmuring, the tortoise given a head start out of simple fairness, its clawed feet inching forward in that unhurried, deliberate way tortoises have always moved, as if time itself were something they'd already made peace with. Achilles, sandals laced, muscles loose, begins his pursuit. Common sense says he'll catch up easily and pass the tortoise within moments, the way any of us would expect a sprinter to overtake a garden snail without a second thought. But Zeno asks you to slow the picture down, frame by frame, the way you might watch dust drift through a shaft of late afternoon light. Before Achilles can catch the tortoise, he must first reach the point where the tortoise started. By the time he arrives there, though, the tortoise, however slowly, has shuffled a little farther on. So Achilles must then close that new gap. But by the time he does, the tortoise has crept forward again, if only by a hair's width, a shadow's width. This goes on, an endless sequence of smaller and smaller gaps, each one needing to be crossed before the next can even be attempted, like nested boxes that keep opening onto smaller boxes no matter how many you unpack. And so, Zeno concludes, quick-footed Achilles can never actually catch the plodding tortoise at all, because there is always one more gap waiting between them, world without end. There's a companion paradox, sometimes called the dichotomy, that strips away the race entirely and leaves just you, walking across your own bedroom toward the door, or maybe toward the switch that turns off the last light of the evening. To reach the door, you must first walk halfway there. Once you've done that, you must cover half of what remains, then half of what remains after that, and half of what remains after that, forever. Each half step is a real distance, however small, and there is always another one waiting behind it, patient and undiminished, however far you've already come, however tired your legs, however close the door seems to your eyes. Under this kind of scrutiny, it starts to look as though you can never finish crossing the room. It starts to look, honestly, as though you can never even begin, since before covering the first half, you'd need to cover half of that half, and half of that, all the way down into distances too small to picture, like grains of sand shaved endlessly thinner, or like a single drop of water divided and divided until it seems to vanish from thought altogether without ever quite reaching nothing. Zeno's paradoxes irritated the Greeks precisely because they weren't tricks, weren't clever wordplay meant to score a debate. Nobody seriously doubted that Achilles would win the race, or that you could cross your own bedroom to blow out a candle and settle under the blankets. The puzzle was that pure logic, followed patiently and honestly, step by careful step, seemed to forbid something everyone had just watched happen 1,000 times, something as unremarkable as a person walking from one side of a room to the other. Something in the reasoning had to be wrong, and yet for a very long time nobody could quite locate the flaw, and that unlocatable flaw is what needled at philosophers for centuries afterward, passed down like a stone in a shoe that nobody could quite shake loose. It's part of what made later thinkers, the ones we touched on a moment ago, so wary of infinity as anything more than a process glimpsed from a safe distance, something to gesture toward but never quite hold. If merely imagining an infinite number of steps could apparently stall a warrior mid-stride, freeze him there in the dust forever, then infinity, actually gathered and completed, seemed like dangerous company to keep, the kind of idea you nodded politely at and then quietly avoided inviting into serious mathematics. The real difficulty, it turns out, hides in a quiet assumption almost too obvious to notice, the assumption that infinitely many steps must take infinitely long to finish. It feels obvious because in ordinary experience, more steps generally means more time. Walk to the mailbox in 10 strides and it takes some measured span of seconds. Walk there in 1,000 tiny strides, each one about the same size and taking about the same fraction of a second, and the total time balloons accordingly, stretching out the way a task always seems to stretch when you break it into too many small pieces. But Zeno's steps aren't ordinary equal strides. They're halves. Each one is exactly half the size of the one before it, and, if you're moving at a steady pace, each one also takes exactly half the time of the one before it. And this is where something remarkable quietly happens, something the Greeks sensed but didn't yet have the tools to state cleanly, something that would take many generations of careful thinking to finally pin down. If a first half step takes, say, half a minute, the next quarter step takes a quarter of a minute, the following eighth step takes an eighth of a minute, and so on, then even though there are infinitely many of these shrinking intervals of time, they don't pile up into an infinite total. Half a minute, plus a quarter minute, plus an eighth, plus a 16th, on and on without ever stopping. Added together, the whole endless sum settles, gently and precisely, on exactly 1 minute. Not almost 1 minute. Not approaching 1 minute forever without arriving, circling the number the way a moth circles a lamp without ever landing. 1 minute, no more and no less, the way a cup of tea left on a nightstand cools by smaller and smaller degrees each passing moment yet still, eventually and completely, reaches the temperature of the room around it, no longer warm, no longer changing, simply and finally settled. This is what mathematicians would later call a convergent series, and even though the formal machinery for describing it properly didn't arrive until many centuries after Zeno, the underlying pattern was not entirely unknown even in the ancient world. Archimedes, working roughly 200 years after Zeno and living in Syracuse on the island of Sicily, a city of harbors and shipyards, and, by his own reputation, at least one memorable bathtub, used exactly this kind of shrinking, endlessly repeating sum to calculate the area trapped inside a curved shape called a parabolic segment. He built the area out of an ever finer mesh of triangles, fitting each new, smaller triangle into the sliver of space its predecessor had left uncovered, and he found that each new layer of triangles contributed only a quarter of the area the previous layer had contributed. Then, through a careful method of his own invention, one he called, with a kind of dry modesty, the method of exhaustion, since it exhausted the remaining space rather than claiming to leap over it, he showed that this infinite stack of ever smaller triangular slivers added up to a perfectly finite, perfectly ordinary number, a number you could write down and hand to someone. Archimedes didn't have the word convergence, and he certainly didn't have anything resembling modern calculus, which was still nearly 2,000 years away. But he had, in effect, tamed an infinite process, using nothing more than patient bookkeeping and a healthy suspicion of shortcuts. It's a lovely, quiet kind of achievement, the mathematical equivalent of counting sheep, so carefully, so evenly, that you notice, almost without meaning to, that the flock never actually needed to be infinite for the counting itself to settle you gently into sleep. So the resolution to Zeno's puzzle, once people were finally ready to hear it, wasn't that motion is impossible, and it wasn't that Achilles really does lose to the tortoise after all, out there somewhere on that sunlit track. The resolution was that infinitely many steps can add up to a perfectly finite journey, finished in a perfectly finite stretch of time, so long as those steps keep shrinking fast enough as you go, faster than the mind's first instinct expects. The room really does have infinitely many halfway points between you and the door, in some strict mathematical sense, waiting there quietly whether you notice them or not. But that infinity lives comfortably inside a single, ordinary, finite walk across the carpet, the way an entire lifetime of relaxed, unhurried breaths can fit inside one quiet, dimming evening. Centuries after Archimedes had finished his patient bookkeeping in Syracuse, another Italian, working in a very different century, found himself troubled by a puzzle that felt, on the surface, almost childish. Galileo Galilei, in the last years of his life, under house arrest near Florence, wrote a book called Two New Sciences, and tucked inside it, almost as a digression, is a small and strange observation that would end up waiting nearly 250 years for anyone to take it fully seriously. Galileo noticed something about whole numbers. Take the counting numbers, 1, 2, 3, 4, 5, stretching out forever, and take just the square numbers hiding inside them, 1, 4, 9, 16, 25, also stretching out forever. It seems obvious, doesn't it, lying here in the dark, that there should be far fewer square numbers than counting numbers. After all, most numbers aren't perfect squares. Between 1 and 100, there are only 10 square numbers, and 90 numbers that aren't squares at all. The squares seem sparse, thinned out, like street lamps spaced farther and farther apart as a road runs on into the distance. And yet Galileo noticed that every single counting number, without exception, has exactly one square that belongs to it, and every single square number, without exception, comes from exactly one counting number. 1 goes with 1, 2 goes with 4, 3 goes with 9, 4 goes with 16, 5 goes with 25, and so on, forever, each number on one list finding its unique, unshared partner on the other list, with nobody left over on either side, no matter how far you walk down the two columns. So which is it? Are there fewer squares than counting numbers, because the squares are so obviously a smaller, thinner piece of the whole? Or are there exactly the same number of squares as counting numbers, because you can pair every single one up perfectly, with no leftovers on either side? Galileo sat with this for a while, turning it over the way you might turn over a smooth stone in your pocket on a long walk, and in the end he didn't try to force an answer. He simply concluded that the ordinary words we use for comparing sizes, words like more and fewer and equal, words that work perfectly well for finite piles of apples or finite flocks of sheep, simply stop making reliable sense once a collection goes on forever. He didn't resolve the paradox. He named it, gently set it down on the table, and moved on to other problems, the way you might set aside a difficult thought before sleep, trusting that it will still be there, patient and unharmed, whenever you're ready to pick it back up. And for a long time, almost nobody did pick it back up. It sat quietly for generations, treated as one of those charming oddities that clever men occasionally stumbled into and just as wisely left alone. It wasn't until the later part of the 1800s that someone came along willing to take Galileo's small, uneasy observation and push on it, hard, until it gave up its secret. That someone was Georg Cantor, a mathematician born in St. Petersburg in 1845, who spent most of his working life at the University of Halle in Germany, a respectable but not especially prestigious school, somewhat off to the side of the grand mathematical centers of Berlin and Göttingen. Cantor was, by most accounts, a restless and intensely serious thinker, prone to long stretches of both dazzling productivity and difficult depression, and he had a habit that many of his more cautious colleagues found unsettling. He liked to ask what would happen if you simply took an idea seriously and followed it all the way to the end, instead of stopping politely at the point where common sense started to complain. Cantor's move, the one that would eventually change how mathematicians think about infinity forever, was to take Galileo's uneasy little pairing trick and turn it from an embarrassing curiosity into a precise, working definition. Instead of asking, vaguely, whether one infinite collection is bigger than another, Cantor proposed something sharper. He said, let's define two collections as being the same size, exactly the same size, if and only if you can match up every member of the first collection with exactly one member of the second, with nothing left over on either side and nothing doubled up. This is called a one-to-one correspondence, and for finite collections it matches perfectly with our everyday intuition. If you can pair every fork in a drawer with exactly one spoon, with no forks left over and no spoons left over, then you have the same number of forks as spoons, and nobody needs any deeper theory to be convinced of that. Cantor's insight, the quiet, almost audacious insight, was to say that this same test, this same simple act of pairing, should be trusted just as fully when the collections go on forever, even when it leads to conclusions that feel, at first, faintly absurd. And by that test, Galileo's squares really are, in a perfectly rigorous sense, exactly as numerous as the counting numbers themselves. Not almost as numerous, not a smaller infinity trying its best to keep up. Exactly the same size in the only sense that Cantor's definition allows us to speak precisely about size at all, once a collection has stopped being finite. The part matches the whole, one for one, forever, and there is nothing hiding, nothing missing, nothing left dangling at either end. Once you let yourself sit with that for a moment, other examples start to surface, almost on their own, the way shapes in a dark room become clearer the longer you let your eyes adjust. Think about the even numbers, 2, 4, 6, 8, stretching out endlessly. It feels, at first glance, exactly like the square numbers did, like it should obviously be half as large as the full set of counting numbers, since after all, you're throwing away every odd number along the way. But pair each counting number with its double, 1 with 2, 2 with 4, 3 with 6, 4 with 8, and again, you get a flawless one-to-one correspondence, every counting number claiming exactly one even number, every even number claimed by exactly one counting number, nobody excluded, nobody duplicated. The even numbers, by Cantor's careful test, are exactly as numerous as all the counting numbers combined, evens and odds together. Half of infinity, it turns out, is not smaller than infinity. It is, in this very particular and carefully defined sense, infinity itself, wearing a different coat. This is, understandably, the point where a lot of people start to feel a little dizzy, a little suspicious that some kind of trick is being played on them, some sleight of hand hidden in the pairing. It can help, here, to remember that nothing about the individual numbers has changed. 2 is still smaller than 4. There are still, in any ordinary stretch you might name, twice as many counting numbers as even numbers, if you stop and count them up to some particular finite point and compare the tallies. What Cantor discovered isn't that these local, everyday intuitions about size are wrong. It's that they simply don't extend, without modification, to collections that never stop. Size, for infinite collections, has to be redefined from the ground up, using the one tool that survives the trip intact, which is this business of pairing things off, one against one, and asking only whether anyone gets left standing alone at the end. It's a bit like discovering that the rules you use to compare the weight of 2 stones don't quite work anymore once you're trying to compare 2 different kinds of endless rivers, and that you need an entirely different, more careful kind of scale, one built for a different sort of question altogether. And it's that same delicate scale, once Cantor had built it, that would soon let him ask an even stranger question, one that would take him from matching whole numbers against their own subsets to wondering whether every infinity, once you tested it carefully enough, really does turn out to be the same size after all. Let's follow that same scale a little further, because the counting numbers and their evens were really just a warm-up, a gentle first stretch before the more interesting bends in the road. Once you've accepted that pairing things off, one by one, forever, is the real test of infinite size, you start to wonder what else might survive that test. What about the integers, for instance? Not just the counting numbers, 1, 2, 3, marching off in one direction, but the whole family, including 0, and including every negative number stretching away in the other direction, -1, -2, -3, all the way out. Surely, you might think, lying there picturing a number line stretching endlessly in both directions from a lit window in the middle, surely this doubled, two-sided infinity has to be bigger than the plain counting numbers, which only ever march forward. It has, after all, 2 entire directions to fill instead of 1. It feels roughly twice as generous. But remember what happened with the evens. Intuition about doubling and halving, about more and fewer, was exactly the sense that broke down once things stopped stopping. So before trusting that feeling, the honest thing to do is run the same test Cantor ran. Try to build a pairing, a careful hand-holding, between the counting numbers and the integers, and see whether anyone gets left over. It turns out you can. You just have to be a little clever about the order in which you list things, rather than trying to march through them in the shape they naturally seem to want. Instead of listing the integers as they sit on the number line, sweeping from negative infinity up through 0 to positive infinity, you list them by hopping back and forth from the center outward. 0 first, then 1, then -1, then 2, then -2, then 3, -3, and so on, a gentle oscillation, out and back, like someone standing at a doorway leaning first into one room and then into the room across the hall, alternating, never staying on one side too long. Every single integer, no matter how large or how deeply negative, eventually gets a turn in this list. Give me any integer you like, say -47, and I can tell you exactly which counting number it's paired with, exactly which position in the list it occupies. It's a specific, findable, finite position, even though the number itself might feel, at first glance, buried somewhere in an infinite negative direction. Nothing is truly buried. Everything surfaces, eventually, if you wait long enough and count carefully enough. So the integers, doubled infinity and all, turn out to be exactly the same size as the plain counting numbers. Not smaller, not larger. The same. This is the first hint that something even stranger might be true. That maybe this particular size of infinity, the one the counting numbers represent, is remarkably hard to outgrow. Mathematicians eventually gave this size a name, a word borrowed with a kind of quiet reverence from the Hebrew alphabet, Aleph Nul, Aleph being the first letter, and the little 0 marking it as the first and smallest in what would turn out to be an entire family of infinite sizes. Aleph Nul, the size of the counting numbers. The size, as we've now seen, of the evens and of the integers too. Now, here is where things get genuinely strange. Strange enough that it's worth sitting with slowly, the way you might turn over a smooth stone in your palm in the dark, feeling its shape before deciding what it is. Consider the fractions. Not just any fractions, but all of them. Every possible ratio of one whole number to another. 1/2, 1/3, 2/3, 17/41, anything you could write as one integer sitting on top of another. Mathematicians call this collection the rational numbers, and there's something about them that seems, on its face, wildly more crowded than the plain counting numbers ever were, because between any two counting numbers, say between 3 and 4, there is nothing else. No counting number squeezes in between them, but between any two fractions, no matter how close together they already sit, there is always another fraction waiting in the gap. Between 1/2 and 1/3, there's 5/12. Between 5/12 and 1/2, there's another fraction still, and between that one and 1/2, another, and so on, forever, no matter how far you zoom in. Mathematicians call this property density, and it means that fractions don't sit in a neat, evenly spaced row the way counting numbers do. They swarm. They cluster infinitely close to one another, so close that you could never even say, with any confidence, which fraction comes right after 1/2, because there simply isn't one. There is always another fraction squeezed in between any two you might propose, forever, without end. Given that, it would be entirely reasonable to guess that the fractions must be a bigger infinity than the counting numbers, vastly bigger, since between any two counting numbers there's nothing, and between any two fractions there's everything, an entire infinite crowd. And yet, when Cantor sat down and actually tried to build a pairing, a genuine one-to-one hand-holding between the counting numbers and all the fractions, he found, almost unbelievably, that it could be done. Every single fraction, no matter how it's written, no matter how enormous its numerator or denominator, can be given its own specific spot in an infinite list, its own specific counting number to be paired with, so that nobody is left out and nobody is counted twice. The way to see this is to imagine, instead of a straight line, something more like a grid, a great sprawling table stretching out in two directions, with the fractions arranged so that every one, in its top row, gives the fraction 1 over that number, 1 over 1, 1 over 2, 1 over 3, and in the row below, 2 over that same number, and below that, 3 over that number, and so on, forever, in both directions, a table wide enough and tall enough to eventually contain every possible fraction somewhere within it. Now, instead of trying to walk through this grid row by endless row, which would never let you finish even the first row, you walk through it diagonally. You start in the corner at 1 over 1, then you take the short diagonal that catches 1 over 2 and 2 over 1, then the next diagonal, a little longer, catching 1 over 3, 2 over 2, 3 over 1, then the next diagonal after that, longer still. Each diagonal is only a finite little stripe, easily counted, easily finished, and by sweeping through diagonal after diagonal, corner to corner, you eventually pass through every single square in that infinite grid, every single fraction, each one landing at some specific, countable position in your list. A few of the fractions repeat, since 2 over 2 and 1 over 1 both equal 1, but repeats are easy enough to skip past once you notice them, simply moving on to the next new fraction in the diagonal sweep. What you're left with, once the repeats are quietly stepped over, is a complete, orderly list of every fraction there is, each one paired with its own counting number, this 1/3, that 1/17, this one 2, in a definite countable order. So despite feeling infinitely more crowded, infinitely denser, the fractions turn out to be exactly the same size of infinity as the plain counting numbers. Aleph Null again, the same modest first infinity, wearing yet another coat. It's a genuinely peculiar thing to sit with in the dark, that a collection with no gaps at all, a collection where you can always find something new squeezed between any two members no matter how close, can still, somehow, be laid out in a single, patient, countable line, one item following another, forever, without anyone truly getting lost. And once you've absorbed that particular surprise, you might start to wonder, quite reasonably, whether every infinity really behaves this way in the end, whether this diagonal trick, this careful weaving through a grid, might eventually let you count anything at all, no matter how impossibly dense or tangled it first appears. And yet it doesn't. Somewhere in the 1870s, a mathematician named Georg Cantor, working quietly at the University of Halle, in what was then a fairly minor German town, sat down with a question that seems almost embarrassingly simple on its surface. He wanted to know whether the real numbers, not just the fractions, but every possible point on the number line, including all those restless, non-repeating decimals like pi and the square root of 2, numbers that never settle into a pattern no matter how far you follow them, could be counted in the same way the fractions had just been counted, whether they, too, could be lined up, one after another, matched against 1, 2, 3, 4, forever, without anyone being left out. To make the question more manageable, Cantor didn't try to count all the real numbers at once. He narrowed his attention to just the small stretch between 0 and 1. It sounds almost like cheating, focusing on such a modest little sliver of the number line, barely a hand's width if you pictured it as a ruler. But that sliver, it turns out, already contains infinitely many numbers, and if you can show something strange happens even there, in that narrow window, you've shown something true of the whole endless line beyond it. Think of it a little like testing whether a single cup of water from the ocean tells you something about the whole ocean. Sometimes a small sample really does carry the whole truth inside it. So imagine, if you will, that someone claims to have made a complete list of every real number between 0 and 1. Every single one, no exceptions, each written out as an infinite decimal, and each one assigned its own position in the list. A first number, a second, a third, continuing on forever, the same way you might imagine an endless column of names filling an endless ledger. The person making this claim believes, quite sincerely, that they've captured everything, that there is no number between 0 and 1 that isn't already sitting somewhere in their list, waiting its turn. Cantor's insight was to show that no matter how carefully anyone builds such a list, no matter how clever or exhaustive they try to be, there will always be a number they missed, not a number that was simply forgotten and could be added in with a little more effort. A number that, by its very construction, cannot appear anywhere on the list at all. Not at position 1, not at position 1,000,000, not at any position whatsoever, however far down you look. Here's how you'd build that missing number, and it helps, in the dark, to picture it almost like a piece of quiet needlework. Take the first number on the list, and look only at its first digit after the decimal point. Change that digit to something different. It doesn't much matter what. Just pick some simple rule. Say, if the digit is a 5, make your new digit a 6, and otherwise make it a 5. Now take the second number on the list and look only at its second digit. Change that one too, by the same simple rule. Move to the third number and change its third digit. The fourth number, its fourth digit. On and on, forever, moving diagonally down through the list, touching the first digit of the first number, the second digit of the second number, the third digit of the third, always advancing one step further down and one place further to the right, like a needle drawing a single continuous thread along the diagonal of an infinite quilt. When you're finished, and in a strange, patient way, you are always finished, even though the process never technically ends, because every single digit of your new number does get decided, eventually, by this rule. You have built a brand new decimal number, sitting somewhere between 0 and 1. And here is the quiet, devastating part. This new number cannot be the first number on the list, because it differs from that number in the very first digit. It cannot be the second number, because it differs from that number in the second digit. It cannot be the third, for the same reason at the third digit, nor the fourth, nor the 400,000th, nor any number at all on the list, however far down you search, because at whatever position you check, the new number was specifically, deliberately built to differ from the number sitting at that exact position in that exact digit. So this new number, this quiet diagonal creation, is guaranteed to be absent from the list, not accidentally overlooked, the way a name might slip through the cracks of a badly kept ledger, but structurally, necessarily excluded by the very method used to build it. And this holds true no matter which list you started with. Give Cantor's argument any list at all, any attempt whatsoever to enumerate the real numbers between 0 and 1, and it will hand you back a specific number, built from that very list that is guaranteed not to appear on it, which means no list, however long, however cleverly constructed, can ever be complete. There will always be a real number left out. Compare this to what happened with the fractions. There, when Cantor swept through that infinite grid on the diagonal, he found a way to catch every single fraction, eventually, no matter how long it took. The diagonal sweep was a tool for completeness, for gathering everything in. Here, with the real numbers, the diagonal does something almost the opposite. It becomes a tool for proving that completeness is impossible, that something will always slip through no matter how the list is arranged. The same geometric idea, a diagonal line cutting across rows, produces two entirely different verdicts, depending on what it's applied to. It's a little like discovering that the same key opens one door and firmly, permanently locks another. And so the real numbers between 0 and 1, that narrow little sliver of the number line, turn out to represent a larger infinity than the counting numbers themselves. Not larger the way a bigger crowd is larger than a smaller one, since both crowds here are already infinite, already endless. Larger in the sense that no matter how you try to pair the real numbers off against the counting numbers, 1 to 1, first to first, second to second, some real numbers will always be left standing outside the pairing, unmatched, uncounted. Mathematicians eventually gave this larger infinity its own name and its own symbol, distinguishing it clearly from the modest, patient aleph null of the counting numbers and the fractions. This new infinity is called uncountable, and it belongs to what's sometimes referred to, a little poetically, as the continuum, the seamless, gapless stretch of the real number line itself. It's worth sitting with how strange this really is, there in the quiet. The whole numbers go on forever. The fractions, despite being infinitely denser, packed infinitely tighter, still go on forever in exactly the same way, countable, listable, no larger than the whole numbers themselves. But the real numbers, once you include all those wild, non-repeating decimals filling in every last gap between the fractions, form an infinity of an entirely different order, a bigger kind of endless, one that resists being captured in any list at all. When Cantor first published this result, many of his fellow mathematicians found it almost impossible to accept, a strangeness bordering on absurdity. But the argument itself was airtight, each step following calmly from the last, and it would eventually open the door to an even stranger question still, one worth approaching slowly, gently, the way you'd approach the edge of very deep water. If infinity can already come in at least two different sizes, one countable and one not, is there any reason to believe it stops there, at just two? The answer, it turns out, is no. There's no reason at all to think two sizes are the limit, and once Cantor asked the question, the universe of infinities cracked open even further, revealing something closer to an endless staircase than a simple pair of steps. Here's the piece that makes it work, and it's a strangely simple idea once you sit with it. Take any collection of things, any set at all, and imagine gathering up all its possible subsets, every way of selecting some, none, or all of its members. Mathematicians call this the power set. If you have a set of 3 items, say a cup, a spoon, and a candle, the power set includes the empty selection, each item alone, each pair, and all 3 together, 8 subsets in total, from 3 original items. And Cantor showed, through a proof with the same quiet, relentless logic as his earlier one, that the power set of any set is always strictly larger than the set you started with. Always. It doesn't matter how large the original set is, doesn't matter if it's already infinite, already endless. The collection of its subsets is bigger still. No pairing, no matching, No clever correspondence will ever succeed in lining the two up evenly, 1 to 1. Think about what that means, lying there in the dark. Apply it to the counting numbers, and you get something larger than Aleph Null, the modest infinity of 1, 2, 3. Apply it again to that new, larger infinity, and you get something larger still. Apply it a third time, a fourth, forever, and there is no ceiling, no final size, no last and largest infinity waiting at the top, like a roof over the staircase. Every infinity, once you have it in hand, generates a bigger one standing just behind it, patiently, the way a shadow follows a shape. There isn't one infinity or two infinities. There's an endless tower of them, each rung taller than the last, going up and up without any place to stop and rest. Mathematicians eventually needed a way to name all these different sizes, to keep them straight, and they reached for a letter from the Hebrew alphabet, Aleph, the same alphabet Cantor himself had grown up reading, since he came from a family with Jewish heritage on his father's side, though he was raised and remained Lutheran his whole life. The smallest infinite size, the size of the counting numbers, became Aleph Null, Aleph Naught, that patient, listable infinity we've already spent time with. The next size up, whatever it turns out to be, is Aleph 1, then Aleph 2, Aleph 3, climbing the staircase rung by rung, each one representing a strictly larger flavor of endless. And here's where the story gets genuinely strange. Strange enough that it troubled its own inventor for the rest of his working life. We know the real numbers, that whole seamless continuum stretching along the number line, form an infinity, larger than Aleph Null. We know that for certain, proven, settled. But which infinity is it exactly? Is it Aleph 1, the very next size up the staircase, sitting immediately above the counting numbers with nothing in between? Or could it be Aleph 2, or Aleph 17, some much higher rung, with other, stranger infinities tucked in the gap between the countable numbers and the real ones, sizes nobody has ever managed to construct or point to directly? Cantor believed, strongly, almost as an article of faith, that the real numbers sat at exactly Aleph 1, the very next step, no gap, nothing squeezed in between. He called this belief the continuum hypothesis, and he spent years, real years of his life, trying to prove it outright, the way he'd proven everything else. He failed. Not for lack of brilliance, but because, as it would turn out decades later, the question itself was built differently from the questions he'd answered before. The effort weighed on him. Cantor suffered from what appears to have been a form of depression, worsening over time, and he spent periods of his later life in a sanatorium in Halle, the German city where he taught for most of his career, all while feeling professionally isolated, since some of the most influential mathematicians of his day, particularly Leopold Kronecker, dismissed his work on infinity as nonsense, even as a kind of mathematical heresy. History has been much kinder to Cantor than his contemporaries were, but he didn't live to see that kindness. He died in 1918, the continuum hypothesis still unresolved. It stayed unresolved for a long time afterward, unresolved enough that in the year 1900, the mathematician David Hilbert, standing before a conference in Paris, listed it as the very first item on his famous list of 23 great unsolved problems he hoped mathematics would answer in the coming century. And answered, in a sense, it eventually was, though not in the way anyone expected, not with a clean yes or a clean no. In 1940, the logician Kurt Gödel showed that the continuum hypothesis could not be disproven using the standard, ordinary foundational rules mathematicians rely on for building the rest of mathematics, a system of axioms called Zermelo-Fraenkel set theory. Then, in 1963, an American mathematician named Paul Cohen went further, showing the reverse as well, that the continuum hypothesis could not be proven from those same standard rules either. Together, these two results settled something, but not the thing everyone expected settling. They didn't tell us whether the continuum hypothesis is true. They told us that it's independent, floating free of the axioms mathematicians normally use, neither confirmed nor denied by them, no matter how long or how carefully anyone searches. It's worth resting on what independence actually means here, since it's easy to mishear it as just another unsolved problem, a locked door someone simply hasn't found the key to yet. It isn't that. It's closer to something like this. Imagine you're given a flat sheet of paper and told to draw a straight line and a point sitting off to the side of that line, and then asked how many other straight lines you can draw through that point that never cross the first one at all. On an ordinary flat sheet, the answer is exactly one, that familiar rule from school. But change the surface, curve it, and the answer changes with it. On a sphere, there's no such line at all. Everything curves back and eventually meets. On a saddle-shaped surface, there are infinitely many. None of these answers is more correct than the others. They're simply different, each one following faithfully from a different starting geometry, a different choice of ground rules. The continuum hypothesis works something like that. Within the standard axioms of set theory, you can add it as true, and the resulting mathematics holds together, consistent, workable, its own coherent universe. Or you can add its opposite instead, and that mathematics holds together too, just as coherent, just as workable, a different universe built on the very same starting ground. The axioms themselves simply don't reach far enough to decide the matter one way or the other. It isn't a gap in anyone's cleverness. It's a genuine gap in the foundation, discovered rather than invented, and mathematicians still don't agree on what, if anything, ought to be done about it. So the size of infinity, whether the real numbers sit at Aleph 1 or somewhere further up that endless staircase, turns out to be a question the ordinary rules of mathematics were never built to answer, one way or the other. And that raises something worth carrying quietly into the next part of this. Something a little different from questions of size altogether. Because so far, every infinity we've touched has been an infinity of numbers, drawn on paper, defined by rules. The next question is stranger, and perhaps gentler to fall asleep inside. Whether anything like this endless, layered strangeness has any real home out there in the physical world at all, or whether it lives only here, in the quiet architecture of thought. There's a hotel that has never existed anywhere except inside the pages of a lecture, and yet it has done more to make infinity feel real, or at least feel graspable, than almost anything else mathematicians have ever dreamed up. The story is usually credited to David Hilbert, the German mathematician who, in the early 20th century, was busy trying to lay unshakable foundations under all of mathematics, brick by logical brick. Hilbert didn't publish this hotel in a paper. As far as anyone can tell, he used it in lectures, a kind of parable he told his students to make the strange arithmetic of infinite sets feel less like sleight of hand and more like something they could stand inside and walk around in. It was another mathematician, George Gamow, who later wrote it down and gave it the shape it has today. But the hotel still carries Hilbert's name, and it still does exactly what he wanted it to do, which is to take an idea that sounds impossible and make it feel, for a few quiet minutes, almost ordinary. Picture the hotel itself first, because the picture matters. It's not unusually strange to look at. Long corridors, doors evenly spaced, A front desk with a bell that gives a small brass ring when you tap it. The only unusual thing is the room numbers. They don't stop. Room 1, Room 2, Room 3, and onward. No final door, no last hallway, no wing where the numbers give out and the building simply ends. Every room is occupied tonight, every single one. The hotel is, in the ordinary sense of the word, completely full. A traveler arrives at the desk, tired, bag in hand, and asks for a room. In an ordinary hotel, a full hotel, that's the end of the conversation. The manager would apologize and suggest trying somewhere down the road, but this manager doesn't apologize. This manager picks up the phone and makes an announcement that reaches every room at once. Everyone, please move from your current room into the room numbered one higher than the one you're in now. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 1000 moves to room 1001. And because there is no last room, no guest is ever asked to move into a room that doesn't exist. Nobody gets displaced with nowhere to go. Everybody still has a room, still has a bed, still has the same view they had a moment before, just one door further down the hall. And when the shuffling settles, room 1 stands empty, freshly available, and the tired traveler checks in and finally gets to put the bag down. Notice what just happened, because it's worth sitting with rather than rushing past. The hotel was completely full, every room occupied, no vacancies, nothing held in reserve, and yet it managed to accommodate one more guest without evicting anyone, without building a single new room, without bending any rule of hospitality at all. That single move, shift everyone up by one, is the whole trick, and it only works because the list of rooms never runs out. In a hotel with a finite number of rooms, the last guest, the one in the final room, would have nowhere to move to, and the whole plan would collapse right there at the end of the hallway. But there is no end of the hallway here. The chain of moves can always continue, because there's always a next room waiting for whoever needs to move into it. Now suppose it isn't one traveler at the desk, but an entire busload. 43 passengers, say, stepping off a coach after a long journey, all needing somewhere to sleep. The manager doesn't panic, doesn't even blink. Everyone currently in the hotel, please move from your room into the room numbered 43 higher than your current one. Room 1 becomes room 44. Room 2 becomes room 45. And so on. The whole hotel sliding 43 doors down the corridor in perfect unison. When the dust settles, rooms 1 through 43 stand open, and the entire busload checks in together, each finding a made bed and a turned-down sheet waiting. But Hilbert, or Gamo telling it on his behalf, wasn't finished, and this next part is where the story stops being a clever party trick and starts revealing something genuinely important about how infinity behaves. Suppose it isn't one bus, but infinitely many buses, an endless line of them pulling up outside. Bus 1, Bus 2, Bus 3, on without end. And suppose each bus carries infinitely many passengers. Seat 1, Seat 2, Seat 3, on without end as well. That's not a large number of new guests. That's infinity multiplied by infinity, showing up at the desk all at once, needing rooms in a hotel that, once again, is already completely full. And somehow, astonishingly, the manager still finds a way to seat every single one of them, using no rooms beyond the ones the hotel already has. The trick this time relies on something mathematicians already understood about prime numbers, though you don't need to know a scrap of that theory to feel why it works. The current guests, all of them, get moved into the rooms whose numbers are powers of 2, 2, 4, 8, 16, on and on, freeing up every other room number in the hotel for the new arrivals. Then the passenger sitting in seat number 2 on bus number 3, say, gets assigned a room number built from those two figures together, using powers of the prime numbers 3, 5, 7, and so on, so that every single passenger on every single bus lands on a distinct room number, and no two passengers, no matter which bus or which seat, are ever sent to the same door. It sounds fussy, written out like that, almost like bookkeeping, but the heart of it is simple and almost beautiful. Every guest, old and new, can be matched to exactly one room, and every room ends up matched to exactly one guest. Nobody doubles up. Nobody is left standing in the lobby. An infinity of infinities checks into a hotel that started out entirely full, and by morning, everyone has slept somewhere. It's tempting to hear a story like this and treat it as pure entertainment. A magician's flourish dressed up in mathematical language, something built to produce a small gasp and then be set aside. But that's not really what the hotel is for, and it would be a shame to let the gasp be the whole point. What Hilbert's Hotel actually demonstrates, carefully and patiently if you let it, is that our everyday intuitions about size, about full and empty, about more and no room left, were built entirely from experience with finite things. Every hotel any of us has ever stayed in has a last room. Every guest list any of us has ever managed has a final name. Those intuitions serve us perfectly well in ordinary life, and there's no fault in them, no failure of common sense. They simply weren't built for a world where the counting never has to stop. Infinity doesn't play by the arithmetic those intuitions rely on, not because infinity is being difficult or perverse, but because it's a genuinely different kind of thing, governed by its own consistent, if unfamiliar, logic. The rules don't break inside Hilbert's Hotel. They just aren't the rules anyone was expecting to find. And there's something almost tender in that, if you sit with it long enough tonight. The hotel never turns anyone away, no matter how many buses keep arriving down that long, unlit road. There's always another room, always a door with a number on it, always a bed being made up somewhere further down the hallway. It's a strange kind of hospitality, endless in a way nothing in waking life ever quite is, and maybe that's part of why it makes such an oddly peaceful thing to picture as your eyes grow heavy, guest after guest sliding quietly one door further along, the whole corridor breathing and resettling, always finding room for one more. There's another room in this same house of ideas, quieter than the hotel, less about guests and doors, and more about distance and approach, and it's worth wandering into now, because it shows infinity behaving in a way that feels almost opposite to the hotel's endless welcome. Picture a line drawn on a page and a curve that comes closer and closer to that line without ever, not once, no matter how far you follow it, actually touching it. Mathematicians call that line an asymptote, and the curve's relationship to it is one of the gentlest, strangest kinds of infinity there is, because it isn't about counting forever, it's about approaching forever. The curve keeps closing the gap. The gap keeps existing anyway. You can walk along that curve for as long as you like, and the space between it and the line will always be there, thinner and thinner, but never gone, like the last light at the edge of the sky just before true dark, always dimming, never quite finishing. Think of it this way, if it helps to picture something more like a room than a graph. Imagine walking toward a wall, and with each step, you cover only half the remaining distance. First, you cross half the room, then half of what's left, a quarter of the original space, then half of that, an eighth, then a 16th, a 32nd, on and on, each step smaller than the last, each one a fraction of a fraction. In principle, If you kept doing this forever, you would take an infinite number of steps and never actually reach the wall. This is old. It's a version of a puzzle first posed by a Greek thinker named Zeno, who lived on the southern coast of Italy around 2,500 years ago in a Greek colony called Elea, and who seems to have delighted in constructing little paradoxes just to watch people squirm. Zeno's runner, in the version usually told, has to reach a finish line, but first must cross half the distance, then half of what remains, forever, an infinite number of tasks stacked between him and the tape. And Zeno's question, dressed up in a foot race, was really this: how can anything ever finish anything if what has to happen first is genuinely without end? For a very long time, this bothered people more than it probably should have, precisely because they were trying to add up an infinite number of steps the way you'd add up a grocery list, one item after another, expecting the total to keep climbing forever if the list never ends. But here's the quiet trick hiding inside that walk across the room. Yes, there are infinitely many steps, but each step is also getting smaller, and it's getting smaller fast enough that the whole infinite parade of them adds up to something perfectly ordinary and finite. Half, plus a quarter, plus an eighth, plus a 16th, and on forever, adds up to exactly 1. Not almost 1. Not a number that creeps toward 1 and stays shy of it forever, the way the curve stays shy of its asymptote. It equals 1, precisely, the same way 2 plus 2 equals 4. This is what mathematicians call a convergent infinite series, a sum with infinitely many terms that nonetheless settles on a single, finite, exact answer. And it's one of the most useful ideas anyone has ever had, because it means infinity, instead of being something to fear or avoid, can actually be tamed into ordinary arithmetic, so long as you know how to look at it. The word mathematicians reach for here is limit, and it's worth turning the word over slowly, because it doesn't mean what it might mean in a sentence like, "There's a limit to how much I can carry." A mathematical limit isn't a wall or a ceiling. It's a destination that a process approaches so closely and so reliably that the destination itself becomes the honest answer to what the process is doing, even if the process, taken step by literal step, never technically arrives. When you say the limit of that halving walk across the room is the wall, you're not claiming that any single step actually touches it. You're claiming something quieter and more useful, that the steps get closer to the wall than any distance you could name, no matter how small, if you're just willing to take enough of them. Name a gap the width of a hair, the walker gets closer than that. Name a gap 1,000 times finer than a hair. The walker gets closer than that too, eventually, given enough steps. The limit is the number that the whole infinite process is quietly aiming at, even while never being asked to actually land on it. This is the piece of mathematics that finally let people handle infinity with confidence rather than dread, and it took surprisingly long to get right. Two men, working independently in the late 1600s, an Englishman named Isaac Newton and a German named Gottfried Wilhelm Leibniz, each built a new kind of mathematics, calculus, meant to describe motion and change, curves and slopes, the speed of a falling object at a single instant rather than averaged over a whole fall. And to do that, both of them found themselves reaching for something they called an infinitesimal, a quantity meant to be smaller than any number you could name, and yet somehow still not quite nothing. It was a strange, almost mystical idea, something like the ghost of a departed quantity, as one of Newton's critics memorably put it, and for well over a century afterward, mathematicians used these infinitesimals productively, built bridges, and predicted the motions of planets with them, all while being quietly uneasy about what an infinitesimal actually was, or whether it was a legitimate mathematical object at all, rather than a convenient fiction. The fix, when it finally arrived, came in the 1800s, largely through the careful work of a French mathematician named Augustin Louis Cauchy and a German one named Karl Weierstrass. And what they did was, in a sense, remove the mysterious ghost quantities altogether and replace them with the language of limits instead. Instead of imagining an infinitely small sliver of distance or time, you could simply ask what value a ratio approaches as an ordinary, finite quantity shrinks closer and closer to zero, without ever needing that quantity to actually become an infinitely small thing sitting there completing the calculation. It was a way of using the idea of infinity, the endlessness of getting closer and closer, without ever needing infinity itself to show up as an object you could point to and hold. The whole apparatus of calculus, derivatives that describe instantaneous change, integrals that add up infinitely many, infinitely thin slices to find an area or a volume, all of it rests on this same quiet foundation, an infinite process tamed into a finite, well-defined answer, approached, but never technically required to be reached. There's a kind of comfort in that, if you let it settle for a moment before drifting further. Mathematics found a way to talk honestly about the endless, the ever smaller, the ever closer, without pretending to have completed something that by its very nature cannot be completed, and without giving up and calling the whole subject nonsense either. It builds a careful, patient bridge to a horizon it never has to actually stand on, and somehow that bridge holds up buildings and satellites and the whole machinery of modern engineering just fine. And it turns out this same trick of getting infinitely close without infinitely arriving isn't confined to graphs and equations at all. It shows up again once you lift your eyes from the page and start asking what infinity might mean out there, in the size and shape of the universe itself. Physicists, it turns out, have their own uneasy relationship with infinity, and it looks a little different from the mathematicians. A mathematician can define infinity carefully, hedge it with limits, and let it live safely inside a proof. A physicist has to ask a harder question. Does this thing I'm describing with an infinite number actually exist out there, in the world made of atoms and light and gravity, or is the infinity in my equation quietly telling me that my equation has run out of things to say? That distinction between infinity as a description of reality and infinity as a red flag warning you that your theory has broken down turns out to matter enormously, and nowhere does it matter more than at the center of a black hole. Picture, if you can hold the image loosely, a star many times heavier than our sun, reaching the end of its life. For millions of years, it held itself up against its own weight by burning fuel in its core. The outward push of light and heat balanced against the inward pull of gravity. A standoff so stable, it barely seemed like a standoff at all. But fuel runs out, and when it does, for a sufficiently massive star, nothing is left to resist the pull inward. The star collapses, not gently, but catastrophically, matter falling in on itself faster and faster, and general relativity, Einstein's theory of gravity, makes a very specific and very strange prediction about where that collapse ends up. It ends up, according to the equations, at a point of zero size and infinite density. Not extremely dense, not almost infinitely dense, infinitely dense, an infinite amount of mass squeezed into no volume at all. This is what physicists call a singularity, and if you say the phrase slowly, singularity, it almost sounds like a place you could visit, a destination, with a name and an address. But most physicists, including Einstein himself, believed that the appearance of infinity here wasn't a discovery about nature so much as a confession from the theory. General relativity was, in effect, raising its hand and saying, "I don't know what happens here. I've run out of road." There's a useful analogy for this, one you can turn over slowly. Imagine you have a very good map of your city, detailed enough to show every street, every building, every tree. It's an excellent map, and it works beautifully almost everywhere. But suppose there's one particular intersection where, if you looked closely at the map, the streets seem to converge into a single point of zero size, with infinite detail crammed into that point, roads folding into roads folding into roads forever. You wouldn't conclude that the actual intersection, the one made of asphalt and traffic lights, is a point of infinite density. You'd conclude, instead, that your map-making method has a flaw, a mathematical artifact that appears at that one location even though the real world there is perfectly ordinary. Most physicists suspect something similar is happening with black hole singularities. General relativity is an extraordinarily successful description of gravity at almost every scale we can test. But at the very center of a black hole, where matter is compressed to scales small enough that quantum effects should matter enormously, general relativity is being asked a question it wasn't built to answer. It doesn't know about quantum mechanics. It just keeps calculating, following its own rules past the point where those rules are trustworthy, and it spits out infinity, because infinity is what happens, mathematically, when you divide by something that keeps shrinking toward zero without a quantum theory of gravity there to catch it. The infinity, in other words, is very likely not a fact about the universe. It's a symptom, a signpost pointing toward missing physics, toward a more complete theory that nobody has finished writing yet, a theory that would presumably replace that infinite point with something finite, strange, and currently unknown. This same pattern, infinity as a warning sign rather than a settled answer, shows up again if you look outward instead of inward, away from collapsing stars and toward the universe as a whole. One of the oldest and most disorienting questions a person can ask, maybe one you've turned over yourself lying awake in the dark, is simply whether space goes on forever. Is the universe infinite in extent, stretching without end in every direction, or is it finite, some enormous but ultimately bounded thing? And here's the first surprise, gentle as it is. Cosmologists genuinely don't know. It's not a settled question, and anyone who tells you with total confidence that the universe is infinite, or that it definitely is not, is speaking with more certainty than the evidence currently allows. What we can observe is limited to what's called the observable universe, a sphere around us roughly 93 billion light-years across, bounded not by any wall or edge, but by the simple fact that light from farther away hasn't had time to reach us yet since the universe began. Beyond that boundary, there may be more universe stretching on and on, possibly forever, possibly looping back on itself in some way too subtle for our instruments to detect, or possibly stopping at some genuine edge we simply cannot see from here. The measurements we've made so far of how space curves on the largest scales are consistent with a universe that's flat, or very close to flat, and a truly flat universe, mathematically, would most likely be infinite. But close to flat isn't the same as certainly flat, and even certainly flat wouldn't fully settle the matter, because a flat universe could still, in principle, be finite if it curved back on itself in more than one dimension, the way the surface of a donut is flat in a local sense, but finite in its overall extent. So the honest answer, the one worth resting your mind on rather than fighting, is that we live inside a bubble of the observable, and outside that bubble, the universe may well continue being ordinary, familiar, star-filled space for a distance so large our own visible patch would look like a single grain of sand by comparison, and we may never, even in principle, be able to confirm whether it stops somewhere or doesn't stop at all. Time carries its own version of this question, and in some ways it's an easier one to hold, though not by much. Did time have a beginning, roughly 14 billion years ago, at the event we casually call the Big Bang, or does it stretch backward forever, with no first moment at all? And looking forward, will the universe simply continue existing, moment after moment after moment, without any final page, expanding and cooling for what our best current models suggest could be an eternity? Here again, physicists have learned to be careful with the word forever, because eternal expansion is a very different kind of claim than eternal in the sense of a number that never ends. It's a prediction built on physics we understand reasonably well, extrapolated across timescales so vast that words like billion and trillion stop being useful, and it may hold up, or it may turn out that something we haven't yet discovered intervenes long before forever actually arrives. The lesson, gathered from black holes and from the edges of space and from the far future of time itself, is a remarkably consistent one. Whenever infinity shows up in a physical theory, whether as a point of infinite density, or an unbounded amount of space, or an endless stretch of time, the wise response isn't necessarily to marvel at having found something truly limitless in nature. It's to ask, quietly and without any particular hurry, whether infinity is really out there, or whether it's simply the shape our current understanding takes at the exact spot where that understanding runs out. There's another place infinity likes to hide, one that has nothing to do with the size of space or the length of time, and it might be worth turning toward now, since it touches something closer to home: the machines we build, the guesses we make, and the messages we send. Consider a computer program, something as simple as a loop that says, count upward, 1, 2, 3, and keep going. Nothing in the code itself tells it to stop. Given enough time and enough electricity, it would keep counting past 1,000,000, past 1,000,000,000,000, past numbers so large they'd take longer to say aloud than the age of the universe allows, and it would never reach an end, because there isn't one to reach. This is a strange kind of infinity, because it isn't a thing sitting out there waiting to be found, the way a distant galaxy is. It's a process, a set of instructions, that simply never terminates. The computer isn't holding infinity in its memory. It's expressing infinity through repetition, the same way you could express it by promising to keep breathing in and out for as long as you're alive, without that promise requiring you to store an infinite number of breaths anywhere. In the 1930s, a young mathematician named Alan Turing, working out of Cambridge, wanted to know something that sounds almost too simple to be hard. Given a program and its starting input, can you always figure out in advance whether it will eventually stop or whether it will run forever? He proved, in a way that still feels startling, that the answer is no. There's no general method, no master algorithm that can look at every possible program and correctly predict, every time, whether it halts. Some programs you can analyze easily. Others hide their behavior so deeply in their own logic that the only way to find out if they stop is to run them and wait, and if they don't stop, no amount of waiting will ever tell you that for certain, because the next step might always be the one that finally ends things. Turing's discovery wasn't really about computers, since the electronic kind hadn't been built yet. It was about the limits of prediction itself, about how even in a universe made of clean, deterministic rules, infinity can slip in through the back door and make some questions permanently unanswerable, not because we lack cleverness, but because the structure of the question forbids a shortcut. Probability has its own quiet relationship with infinity, one that trips people up in a very particular way. Imagine flipping a fair coin forever, an endless sequence of heads and tails stretching out with no final flip. Mathematicians will tell you that the probability of getting heads every single time, forever, is 0. And yet, in the strict logical sense, it isn't impossible. 0 probability and impossibility turn out to be two different things once infinity enters the picture, which feels almost unfair until you sit with it a while. With any finite number of flips, getting all heads is merely unlikely, and the odds shrink and shrink as the flips continue, halving each time, so that by the time you've reached even a few hundred flips, the probability is already smaller than the number of atoms in your body could meaningfully represent. Stretch that shrinking process out to infinity, and the probability doesn't just get very small, it becomes exactly 0, while the outcome itself remains, in the strange bookkeeping of infinite probability, still logically conceivable. This is closely related to an old thought experiment, sometimes called the infinite monkey idea. The notion that a monkey typing at random on a keyboard forever would, eventually, by pure chance, type out the complete works of Shakespeare, not once, but infinitely many times over. It's true, in the mathematical sense, given truly infinite time and a truly random process. But notice how much work that phrase truly infinite is doing. It's a statement about what an idealized, endless process would produce, not a claim about anything that could ever be observed, checked, or waited for by an actual living creature with an actual finite lifespan. The theorem is real. The image of a monkey ever producing Hamlet is not something anyone should picture as remotely realistic. There's a related idea in the world of information, one the Argentine writer Jorge Luis Borges turned into a haunting short story in 1941 about a library containing every possible book. Not every book that has been written, but every book that could be written, every combination of letters and spaces across a fixed number of pages, which means the library contains every true biography ever needed, every accurate history of every event, and also, buried somewhere in its shelves, every possible false version of the same events, along with page after page of pure, meaningless noise, letters strung together with no sense at all. Borges wasn't doing mathematics. He was doing something closer to philosophy, dressed as fiction, but the underlying structure is genuinely mathematical. If you fix a page length and an alphabet, the number of possible books is staggeringly large but still finite, the kind of number that dwarfs the count of atoms in the observable universe many times over without technically being infinite at all. It only becomes truly infinite if you allow the books to be of any length whatsoever, with no upper limit on how many pages a single volume could have. Either way, the story works on the listener the same way infinity so often does, by using an idea that's technically well-defined to produce a feeling that's almost unbearably vast, a library holding the truth about everything and the truth about nothing, indistinguishable from each other unless you already know which is which. Paradoxes like these have a way of feeling like tricks, like someone is playing a game with words to produce a contradiction where none should exist, but most of them are honest reflections of what happens when ordinary intuition, built up from a lifetime of handling finite piles of things, gets applied somewhere it was never designed to go. Take the old puzzle, sometimes called the ball and vase problem. At 1 minute before noon, you put 10 numbered balls into a vase and take one out. At half a minute before noon, you put in 10 more and take one out. You keep halving the time between each step so that infinitely many steps happen before noon arrives, and the question is simply, how many balls are in the vase at noon? If you always remove the lowest numbered ball that's still inside, the vase ends up empty, since every single ball you ever put in eventually gets its turn to be removed. If you always remove a different ball, say the highest numbered one, the vase ends up holding infinitely many balls. Same number of steps, same number of balls in and out at each stage, wildly different outcomes, depending entirely on which ball you happen to pick each time. It isn't that the world is contradictory. It's that the question, what happens at noon, was never fully specified until you decided the rule for choosing which ball to remove. And infinity has a way of magnifying small differences in a setup into enormous differences in the result, the way a tiny error in aim becomes a mile of difference after a long enough flight. What ties all of these together? The halting programs, the endlessly flipped coin, the library of every book, the vase at the stroke of noon, is the same lesson that kept surfacing in physics, just wearing different clothes. Each of these infinities lives comfortably inside a mathematical definition, where the rules are fixed in advance and every consequence follows honestly from them. None of them require you to believe that somewhere out in the physical world there sits an actual infinite library, or an actual coin flipped without end, or an actual vase performing an impossible number of swaps in a finite span of time. They're thought experiments, precise ones, useful ones, but thought experiments all the same, tools for finding out what a concept truly implies once you follow it all the way to its logical edge and refuse to look away. So where does that leave you, lying here, eyes closed, having spent this long walking through vases and libraries and hotels with infinitely many rooms? It leaves you back in a body that is unmistakably finite, a body with a heartbeat that has counted somewhere in the neighborhood of 2 or 3 billion beats by the time it reaches old age, not infinitely many, a specific and countable number, even if no one troubles to count it. A body that will, at some point, stop. Everything you have ever touched, tasted, remembered, or loved fits inside a life with a beginning and an end, a life you could in principle write down, hour by hour, if you had the patience and the paper. Infinity, whatever else it turns out to be, is not the shape of your days. Your days are more like the numbers on a clock face, cycling, finite, returning. And yet something strange happens if you try to talk yourself out of thinking about infinity altogether, the way you might try to talk yourself out of thinking about the ocean, because you'll never see all of it. It keeps sneaking back in, and not as a luxury, not as an idle curiosity for people with too much time on their hands, but as a tool that turns out to be necessary for describing the finite world accurately. Consider something as mundane as drawing a circle. A circle is a perfectly ordinary, finite object. You can trace one with a compass on a napkin in about 2 seconds, but the ratio of its circumference to its diameter, that quiet number pi, cannot be written down completely by anyone, ever, no matter how long they work, or how many digits a computer chews through. It goes on without repeating, forever, and mathematicians have calculated it past 100 trillion digits without exhausting it or finding any pattern that would let it stop. You needed the infinite, in some sense, just to understand the shape of a wheel. The circle didn't ask to be mysterious. It simply is, and the mystery was there all along, waiting under something as ordinary as a dinner plate. The calculus that lets an engineer calculate the stress on a bridge cable or a doctor model how a drug diffuses through the bloodstream was built in the 17th century by 2 men working independently, Isaac Newton in England and Gottfried Leibniz in Germany, and both of them built it out of infinity. Not directly, not by invoking endless libraries or hotels, but by imagining what happens if you take a small change and shrink it again, and keep shrinking it toward nothing, without ever quite reaching nothing. watching what value the whole expression settles toward as that shrinking continues without end. That settling toward a value, without ever fully arriving, is what mathematicians call a limit, and it is the quiet workhorse underneath nearly all of modern science and engineering. Every time a weather model predicts tomorrow's rain, every time a rocket's trajectory gets calculated before launch, every time a heart monitor's software interprets the shape of a pulse, some piece of that infinite machinery, built on ideas about endless smallness and endless refinement, is turning in the background, unnoticed, the way the gears of a watch turn beneath its face while you only ever look at the hands. So infinity earns its keep. It is not decoration. It is not a philosopher's toy kept in a drawer for rainy afternoons. It is closer to a kind of extreme case, a horizon you calculate toward even though you will never stand on it, the way a sailor uses the North Star to hold a course without ever expecting to sail up and touch it. You do not need to reach infinity for it to be useful. You only need to know it is there, fixed, reliable, so that you have something steady to aim your finite calculations toward. But here is the part worth sitting with as your thoughts get looser and slower, the part that separates good thinking about infinity from bad thinking about it. Not everything that feels infinite, in that loose, everyday, half-poetic sense, actually behaves like the mathematical infinities we've spent all this time examining. When someone says their love is infinite, or the night sky feels infinite, they are reaching for a feeling, an overwhelming sense of scale or devotion that ordinary finite words don't quite capture, and that reaching is honest and human and doesn't need correcting. But the actual, provable size of the universe you can observe, the one astronomers can measure with light and radio telescopes, is finite, because light has only had about 13.8 billion years to travel since the early universe became transparent to it, and nothing, as far as anyone has ever measured, travels faster than light. Whether space itself continues on forever, past that observable boundary, or loops back on itself, or simply stops meaning anything as a question past a certain point, nobody currently knows, and it's worth being honest that they don't know, rather than quietly assuming the answer just because the sky looks endless from where you're lying. That honesty matters more than it might seem. Throughout this whole slow walk through infinite hotels and infinite decimals and infinite libraries, the goal was never to hand you a single tidy answer about what infinity really is, underneath everything, once and for all. Mathematicians themselves don't have that single answer, not because they haven't tried hard enough, but because infinity turned out to be less like one thing waiting to be discovered and more like a set of careful, different definitions, each built for a different purpose, each internally consistent, and each of them, when compared directly, revealing something genuinely surprising about how size and counting and endlessness actually work. Georg Cantor, the man who first proved that some infinities are provably larger than others, using nothing but pure reasoning about lists and diagonals, was ridiculed for it during his own lifetime by some of the very colleagues who should have understood his proof best. He spent time in and out of sanitariums, partly for reasons that had nothing to do with his mathematics, and he died in 1918, in one of them, not knowing that within a few decades his ideas about the hierarchy of infinities would become an accepted, foundational part of how mathematics understands itself. Sometimes the strangest ideas need the most patience before the world catches up to them, and Cantor's ideas needed quite a lot of patience indeed. What remains, after all of it, the paradoxes and the proofs and the hotels with their endlessly shuffling guests, is something almost comforting rather than dizzying, if you let it settle that way. You don't need to resolve infinity to live well within a finite life. You don't need to know whether space goes on forever or whether numbers secretly end somewhere no one has found yet in order to notice that the tea has gone cold, or that the room is quiet, or that your breathing has slowed without your really trying to slow it. Infinity is a tool for thinking clearly about things too large or too small, or too endless to hold in your two hands at once. Nothing more mystical than that, and nothing less useful either. You can set it down now, the way you'd set down a book you've been reading by lamplight, mark your place if you like, and let the rest of it wait until some other night, some other slow, unspooling hour when your mind wants company again. For now, there's only this: the dark around you, finite and familiar, the weight of the blanket, real and countable in its small, comfortable pressure, the next breath, and then the one after that, each one arriving in its own good time, each one enough. Rest well.